In this video, we're going to start the KutaSoftware Infinite Pre-Calculus Free Worksheet Approximating Area Under a Curve. Now in numbers 1 and 2, it states, for each problem, approximate the area under the curve over the given interval using 4 left endpoint rectangles. So quickly we can see that depicted in number 1. We have 4 left endpoint rectangles, meaning that the top left corner of those rectangles are points along the function. Now for number 1, our interval is from -2 to 6. So you can see that if we're going from -2 to 6, the change in x, 6 minus -2, is a positive 8. So we need to have 4 rectangles of even widths over the interval of 8. So what we're going to do, we're going to take 8 divided by 4, and that's going to be 2. So you can see each of these rectangles has a width of 2. Now our first rectangle has a height of 2, our second rectangle has a height of 4, our third rectangle has a height of 6, and our last rectangle, our fourth rectangle, has a height of 1, 2, 3, 4, 5, 6, 7, 8. Now remember, in our directions, we're approximating the area under the curve using those rectangles. So we need to find the area of each rectangle and then add them together. In other words, summing them up. So we have, for number 1, 2 times 2. That's our first rectangle. We're adding that to our second rectangle area of 2 times 4. Remembering area is length times width, or width times length. Then we're adding that to 2 times 6. And that will get added to our last rectangle area of 2 times 8. 2 times 2 is 4. 2 times 4 is 8. 2 times 6 is 12. And 2 times 8 is 16. So when we add together 4, 8, 12, and 16, we get a total area of 40 units squared. So 40 is our solution for number 1. Now let's take a look at number 2. And number 2, again, remember we're using 4 left endpoint rectangles. So the top left vertex of each of the rectangles fall on or intersect the function. And in this case, each of the rectangles have a width of 1 unit. But now we just have to figure out the heights. And unlike the last problem where the heights all evenly intersected grid lines, so it's easy to tell the y values, we're going to need to plug in these points. So we're going to need to plug in -3 and solve for y. So y equals the opposite of -3 squared over 2 plus 6. So y is going to equal the opposite of -3 squared. Well, -3 squared is a positive 9. So we're going to have -9 halves plus 6. Adding those all over the same denominator, we'll have -9 halves plus 12 halves, because 6 is equal to 12 divided by 2. So simplifying that, we will get a positive 3 halves. So the height or length of our first rectangle is 3 halves. So we're going to have 1 times 3 halves. And we're going to be adding that to the height of our second rectangle, or the length of our second rectangle times the width. So with the width of 1, that's going to be 1 times the height. You can see it intersects a grid line evenly, and that's 1, 2, 3, 4. So a positive 4 for the length. And then we're going to be adding that to the area of the next rectangle, which is 1 times the length, which does not intersect the grid line evenly. So let's plug in our x value and solve for y. For this rectangle, the x value is a -1. So we're going to have y equal to the opposite of -1 squared over 2 plus 6. That's going to be equal to -1/2 plus 6, which all over the same denominator, I'll have -1/2 plus 6 in terms of halves is 12 halves, and that's going to equal negative 1 plus 12, which is a positive 11, over 2. So 11 halves. So the height of our third rectangle is 11 halves. So we'll have 1 times 11 halves for the area. And then lastly, for our fourth rectangle, we can see that we have a height or length of 6. So then we're adding the area of that rectangle, which is 1 times 6. And remember, when we multiply by 1, that's the identity. So we'll have 3 halves, because 1 times 3 halves is 3 halves, plus 1 times 4, which is 4, plus 1 times 11 halves, which is 11 halves, plus 1 times 6, which is 6. Now, as opposed to writing all of these over 2, I know that 3 plus 11 is going to give me an even number, which is divisible by 2. So I'll have 14 halves, and I'll be adding that to, let's sum 4 and 6 together, so that will be 10. 14 over 2 is 7, so I'll have 7 plus 10, which equals 17. So my answer in number 2 is 17. The area of each of the rectangles summed together is 17. Now in numbers 3 and 4, for each problem, we're to approximate the area under the curve over the given interval again, except this time we're going to be using 5 left endpoint rectangles. And it says that we can use the provided graph to sketch the curve and the rectangles, which will be useful when finding the area. So let's go ahead and plot x squared plus 2x plus 3. However, some points we definitely want to know are the left endpoints. And remember, the left endpoint, if we're going over the interval, that means that we're going to have to divide the change in interval by 5 for our 5 rectangles. So if we have 1 minus a negative 4, that's going to equal 1 plus 4, which is 5. And 5 divided by 5 is equal to 1. So each rectangle is going to have a width of 1. So when calculating area, all our widths are equal to 1. But now let's find the height of each of those. And we'll do so by graphing this function. And I'm going to use a graphing calculator, although feel free to use a t-table and put in different points for x and solve for y. So we have x squared plus 2x plus 3 as our function. So I'll go ahead and graph a few separate points to help us draw that curve. One point is negative 4, 11. So we'll have negative 4, 11. Next, I'll do negative 3, which is negative 3, positive 6. So negative 3 in the x, positive 6 in the y. Then I'll do negative 2, which is negative 2, 3. So negative 2 in the x, positive 3 in the y. Then we can see we have a minimum at negative 1, 2. And then at 0, we're at 3. And if you remember, a quadratic is symmetrical. So if we find that line of symmetry, which occurs at the minimum of x equals negative 1, you can see this point, negative 3, 6, is 2 units to the left. So if we move 2 units to the right of that line of symmetry, where we're at 1 in the x, we will still be at positive 6 in the y. Same for the other point, negative 4, 11. That's 3 units, 1, 2, 3 units to the left of that symmetry line. So now we're going to go 3 units to the right of that symmetry line, staying at that same y height, and plot our other point, which is 2, 11. We can double check on this graph. If we go to 2, we are indeed at 11 in the y. I'll go ahead and draw a curve connecting these points. So there's my parabola in number 3. Now I'm just going to need to draw my rectangles. And remember, we're going to have 5 rectangles that are left-handed rectangles, all with an interval of width 1. And since they're left-handed, they're starting at that lower interval on the left-hand side. So my first point was negative 4, 11. So now I'll draw my first rectangle there. My next rectangle, same width. However, that left endpoint, as opposed to having a height of 11, it was a height or length of 6. My next left endpoint is at -2 because we're going 1 unit over, and at -2 our height was 3. And keeping in mind my interval, I'm going from -4 to +1, and I have 5 rectangles. 1, 2, 3, 4, 5. So I have 2 more to draw, each with a width of 1 unit, because the width of my rectangles must be equivalent. So my next rectangle is going to start with its top left vertex at -2, +2. So it has a length of 2. And my last rectangle starts at 0, 3, so it has a length of 3. Now, I'll just calculate the sum of all those areas. So my first rectangle, the area, length times width, or width times length, is 1 times 11. My next rectangle is 1 times 6. My next rectangle has an area of 1 times 3. My fourth rectangle has an area of 1 times 2. And my last rectangle has an area of 1 times 3. And remember, 1 times any number is that number. So 1 times 11 is 11. And then we're adding that to 6, to 3, to 2, and then to 3 again. 11 plus 6 is 17. 17 plus 3 is 20, 20 plus 2 is 22, and 22 plus 3 is 25. So I have an area of 25 units squared for number 3. And then number 4, looking at my interval again, I have a change in x of 5. So 5 divided by 5, since I need 5 rectangles, is equal to 1. So each rectangle is going to have a width of 1, starting that left endpoint where x equals 2. So let's go back to the graphing calculator, or again, feel free to use a t-table. So my function in this case is 5 over x. So you can see I have a little bit of a curve that's only shown in the interval from -8 to -4. So I'll quickly draw that. But what I'm more concerned about is my interval from 2 to 7. So now that I can see what my graph looks like, I'll show you the method of using a t-table. So if I'm plugging in x values, I'm going to solve for my y values, but I want to do so over this interval. And remember, each of the rectangles I'm using are left endpoint rectangles, and it starts at 2. So the y value at 2 is the first length of my first rectangle. The y value at 3, because my width is 1, that is the next length of my next rectangle. So then when we go to 4, that's the third rectangle. At 5, that will give me the fourth rectangle's height. And at 6, that will give me the fifth rectangle's height. But it spans over the interval to 7. However, we do not need the height at 7 because we're using that height at 6, and that's where our interval ends. So, plugging 2 in for x, we'll have 5 over 2. Plugging 3 in for x, we'll have 5 over 3. Plugging 4 in for x, we'll have 5 over 4. Plugging 5 in for x, we'll have 5 over 5, which simplifies to 1. And then plugging 6 in for x, we'll have 5 over x, which is 5 over 6. And we do not need to continue on to find the height at 7 because we have our 5 rectangles starting at 2, going to 3, 4, 5, 6, and then remember that width at 6 is also 1, which does indeed cover the interval. So here we have 1, 2, 3, 4, 5 rectangles. So even though we're not plugging in a value for 7, that is covered within our interval because of our rectangle at 6. So now let's go ahead and plot each of these points. At 2, we're at 5 halves, which is 2 and 1/2. At 3, we're at 5 thirds, which is 1 and 2/3. At 4, we're at 5 fourths, which is 1 and 1/4. At 5, we're at 1. And at 6, we're at 5 sixths. So I'll go ahead and draw a line connecting these points. And if you remember from our graphing calculator, we had a vertical asymptote at x equals 0 because we cannot divide by 0. So that is an infinite discontinuity at that point. Now let's go ahead and draw our rectangles, even though we already know the heights of each. It's just easier to visualize the area when we see those rectangles drawn out. So the area of our first rectangle, if it has a length of 5 halves and a width of 1, 1 times 5 halves is 5 halves. Then we're adding that to 1 times the height or length of our next rectangle, which is 5 thirds, because 1 times 5 thirds is 5 thirds. 1 times 5 fourths is 5 fourths. 1 times 1 is 1, and then is 5 sixths. So there are each of the areas of the 5 rectangles. Because they all had widths of 1, we just took the y value of that left endpoint, and that was the length, and when multiplied by the width, if the width was 1, the area of the rectangle was equivalent to the length. Now you can see that we have 2, 3, 4, and 6 as our denominators, but we want all of these over the same denominator, so what I'm going to do is find a common denominator. 2, 3, 4, and 6 all have a common denominator of 12. So writing 5 halves in terms of 12, in order to go from 2 to 12, we multiply by 6, so 5 times 6 is 30. In order to go from 5 thirds to 12, we multiplied the 3 by 4, so 5 times 4 is 20. So 30 twelves equals 5 halves, 20 twelves equals 5 thirds, 5 fourths, we had to multiply the 4 by 3, so multiplying 5 by 3, that's 15, so 5 fourths is equivalent to 15 twelfths, and then 1 we'll write as 12 over 12, and then finally 6 we multiply by 2 to get to 12, so multiplying that numerator by 12, we'll get 10. So now in our numerator we have 30 plus 20 plus 15 plus 12 plus 10, which gives us 87, and that's all over 12. Now let's simplify. I know that 87 and 12 are both divisible by 3, so dividing the numerator by 3 and the denominator by 3, I'll get 29 over 4, which in decimal form, 29 divided by 4 is 7.25. So 29 fourths, or 7.25 units squared, is our area of the rectangles summed together in number 4. Now lastly, onto our critical thinking question. It asks us to look back at problems 1 through 4. In which problems does the approximated area appear less than the actual area? So let's go back up. You can see that in both 1 and 4, we have giant gaps between our functions and the rectangles drawn. Whereas in 3 and 4, those gaps are a lot smaller. So I'm going to say that I think that the approximated areas for problem 1 and 2 appear to be less than the actual. And then it says, in which problems does the approximated area appear greater than the actual area? Well, I think that's the case for 3 and 4 because you can see we have a lot of area that extends above the curve with the exclusion of these last two rectangles for number 3. And then in number 4, all of those rectangles extend above the curve, making the area seem or appear greater. So in 1 and 2, the area appeared less, and in 3 and 4, the area appeared greater. So far I have that the approximated areas for problems 1 and 2 appear to be less than the actual, and problems 3 and 4 appear greater. And our final question asks, would using more and smaller rectangles improve our approximation or make it worse? Well, let's look back up at number 1. Let's say if we were to use more rectangles, so as opposed to using 4, let's say we used 8. Then, if we were to use 8, you can see that the area becomes more accurate because our gaps are now smaller than what they once were. Therefore, more rectangles would improve our approximation. So more and smaller rectangles would improve our approximation. And it's a little redundant to say more and smaller because if we're looking at the area of more rectangles over the same area, then of course those rectangles would need to have a smaller width, making them smaller. And that wraps up our approximating area under a curve worksheet. If you have any questions, leave them in the comments below. And as always, like, subscribe, and share.